In this screencast, we'll talk about function definition by cases and primitive recursively closed classes of functions. So this is the first theorem in this screencast, but it's actually theorem 5.4 in chapter 3 of Compatibility, Complexity, and Languages by Davis, Wayoker, and Segal. If you are reading this book, that book along, and following other screencasts, that's the reference. So let C be a primitive recursively closed class, and let G and H be in that class, two n-array functions, and let predicate and array predicate also be in C. Then let f be defined of x1 through xn, be defined in terms of g, h, and p as follows. G is equal to g of x1 through xn if p of x1 through xn and h of x1 through xn otherwise. So it's a simple definition by cases. Then f is in C. So let's sketch a proof. So we will express f in terms of g, p, h, and a couple of functions that we already know to be primitive recursive, and hence they are in C because it is primitive recursively closed. So f of x1 through xn equals g times p plus h x1 through xn times alpha of p of x1 through xn. So g is in C, p is also in C. Then the binary multiplication is primitive recursive, so it must be in C. So that part is in C. H is in C, P is in C, alpha of P is composition, alpha is a primitive recursive function, so it is in C, and multiplication, binary multiplication is primitive recursive, so it is in C, so that part is in C, and then the binary addition is also primitive recursive, so it is also in C, so hence F must be in C. And alpha is the function alpha of x is equal to 1 if x is 0, and 0 if x is not equal to 0. So you can watch the previous screencasts for the definition of alpha and the proof that it is primitive recursive. So this is a corollary of the theorem. So let C be PRC, and let G1 through Gm and H be n-array functions that are also in C. Then we will have M predicates, P1 through Pm, and these are n-array predicates that are in C. And for any two Pi and Pj, so P sub I, x1 through xn times P sub j, x1 through xn, the product is equal to 0. So for I < less than j, and j is less than or equal to m, and I greater than or equal to 1. And for all x1 through xn. So in other words, these predicates, m predicates, are pairwise mutually exclusive. So if we take any two predicates, pi, pj, and any permutation, any sequence x1 through xn of natural numbers, then their pairwise product will be equal to 0. So they're pairwise mutually exclusive. They cannot both be 1 for the same sequence of arguments, x1 through xn. So then let's define a new function, f of x1 through xn, as g of 1 x1 through xn if p of 1 x1 through xn, if this predicate is true, and then all the way to g of m x1 through xn if p of m x1 through xn, otherwise h of x1 through xn, otherwise. Okay, so and then if f is so defined, then f is in C. Okay, let's sketch a proof. The proof will go by induction on M. So M is the number of n-ary functions and predicates from 1 up to some finite number. So let M be equal to 1. This is our base case, inductive base case. Then f of x1 through xn is equal to g of 1 x1 through xn if p1 x1 through xn and h of x1 through xn otherwise. And by the previously proved theorem, since g, p, and h are in C, then f is in C. So inductively, let's assume that the statement is true for M. And let's consider the case of m plus 1 functions. For mg's and mp's, let's consider the case that of m plus 1 g's and p's. Remember, p's are pairwise mutually exclusive. So we have g of m, x1 through xm, if p of m, x1 through xn is true, and g of m plus 1, x1 through xn, if p of m plus 1, p sub m plus 1, x1 through xn, and h, x1 through xn otherwise. Okay. Let me grab a different color. So the idea is that we will define a new function, let's say h prime, and combine the last two cases of f, the new definition of f, into h prime, and h prime by this base case is obviously primitive recursive, and then by the inductive hypothesis, f, which is true for m, f is also in C. Oh, I said h prime is primitive recursive. No, I misspoke. H prime is in C. So C is any primitive recursively closed class, and not necessarily primitive recursive. So let h1 through h prime of x1 through xn be defined as g sub m plus 1 x1 through xn if p m plus 1, and then the arguments, and then otherwise h x1 through xn. Then h is in C, is in primitive recursively closed class. And then by the inductive hypothesis, right, f x1 can be defined in terms of, by the inductive hypothesis, f is in C because it can be defined as g1 if p1, gm if pm, and then h prime. And since h prime is in C, then f is in C. So let's do an example. F of x1 through f of x1 and x2 and x3 is equal to x1 plus 2 if x1 less than x2 and x2 times 2 if x2 less than x1 and 2 and 1 otherwise. So this is a primitive recursive function. By the previous theorem. So because all of the functions and predicates and constants, obviously, this is primitive recursive, and 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 this is just a successor of 0. So f is p